Hello everyone, I hope you are enjoying your day off. We are going to finish the notes that we had from yesterday, and then we are going to finish chapter 9, section 3, by looking at something called a paired t-test. So if you remember yesterday, the example we looked at was for break the ice, and we were looking to see if the mean width of the cubes was 29.5. And there was some data that was collected from the cubes, if you recall. 50 cubes, random sample of 50 cubes, and we had some sample statistics on this, and we ran the hypothesis test, and if you remember, our p-value was fairly large, so we failed to reject the null hypothesis, and this meant we had no reason to suspect that the manufacturing process was out of whack. It was quite possible the true mean width of the cubes was 29.5 millimeters. So let's take a look at a confidence interval, and here we can see Fathom's created a 95% confidence interval for us. We have our count, our mean, our standard deviation, our standard error, which, if you recall, is the standard deviation divided by the square root of the sample size. Our confidence level is 95%, and notice they give us the estimate in two ways. They give us the estimate as 29.4874 plus or minus our margin of error, and then they actually do the addition and subtraction for us, and so this is our actual interval down here. So first, we're going to interpret the confidence interval and think about whether this interval gives us the same conclusion as we got with our hypothesis test. And then we're going to interpret the confidence level. So let's start with the confidence interval. So notice that 29.5 millimeters is within this range of values for the population mean width of all cubes. So it's a plausible value since it's contained in the interval. And then actually interpreting the interval, we are 95% confident that the true mean width of cubes is between 29.4609 millimeters and 29.514 millimeters. And this 95% confidence interval is consistent with our alpha value of 0.05. We failed to reject the null. We thought that 29.5 millimeters is a plausible value according to our hypothesis test, and that's consistent with our confidence interval. 29.5 is within this range of plausible values. And then interpreting the confidence level, just so we don't forget how to do that, if we were to take many random samples of size n equals 50 and construct confidence intervals from those different random samples of size 50, then 95% of those intervals in the long run would contain the true mean width of the cubes. So before we go on to talking about paired t-tests, I just want to make sure that you understand how to use the t-table for getting an estimate for a p-value. So let's take a look at some examples to finish that up. So this first one says find a p-value for a test of the null equals mu equals 10 versus mu greater than 10 that uses a sample size of 75. And so we're going to go to our t-table here. And our sample size was 75, so I should use 74 degrees of freedom, but notice 74 degrees of freedom is not on our table. So what do we do? Can we go up to 80? Well, if we went up to 80, that would mean we had a sample size of 81, and we didn't have a sample size of 81. We only had a sample size of, 75. So what we need to do is go down to 60 degrees of freedom. So we're going to take a look at 60 degrees of freedom, and our test statistic value was 2.33. So I'm going to go along the row of 60 degrees of freedom looking for a test statistic value of 2.33. And I don't see 2.33 here, but 2.33 would be between 2.099 and 2.390. So I'm going to scroll up and look at what column headings we have at the top. We have 0.02 and 0.01. So since our test statistic value would be between these two columns, our p-value is between 0.01 and 0.02. So with the 60 degrees of freedom, Our p-value is between 0.01 and 0.02. That was for a one-tailed test, so we just read the p-value directly from the table. But now we have a two-tailed test, so we need to be a little bit more cautious. We have a sample size of 10, so we're going to use 9 degrees of freedom, and our test statistic is negative 0.51. So because our t-table is symmetric, I'm just going to look up positive 0.51 on the table in the row for 9 degrees of freedom. So here we have 9 degrees of freedom, and 0.051 would actually be over to the left of this column. So you might think that our p-value is bigger than 0.25. However, this is a two-tailed test, so we actually need to double that. So our p-value is actually greater than 0.50. So don't forget to double the p-value that you read from the table if you have a two-tailed test, because the table gives us the area in one tail. And this is a two-tailed test, so we need to count that area twice. Now let's take a look at the final topic from Chapter 9, Section 3. And this is working with paired t-procedures, which happens when we have paired data. Paired data occurs when we have two observations on the same individual or one observation on each of two similar individuals. So we have pairs of data and we subtract the values, and then we do our one sample t procedure to perform inference on the mean difference. This might seem a little bit strange right now, but when we go through an example, this will make more sense. So let's take a look at the following example. Is the express lane faster? For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during the week. So right there's our random condition. They went to the same store. It's important they went to the same store, and they bought the same item. However, one of them used the express lane and the other used a regular lane. They decided which lane each of them would use by flipping a coin. So they entered their randomly assigned lanes at the same time, and then each recorded the time in seconds it took for them to complete the transaction. So we have a naturally occurring pair of data here because this is happening during the same time of day, this first observation. So it should be a similar length of time. And notice it was. Notice down here, this very last observation, the times were quite a bit less. Maybe that was not right before the dinner hour, maybe it was the middle of the day, certainly not on a weekend. So what we need to do to run our hypothesis test for this is enter the values in list 1 for the express lane and the values in list 2 for the regular lane. And I've already done this in my calculator. So I do go to Stat, Edit. So here we have the values for list 1 and list 2, and in list 3 I'm going to have the differences. Now I could go through and calculate all these and do 337 minus 342 and 226 minus 472 and so on, but I'm going to go to the very top of list 3 and tell the calculator to calculate that for me. List 1, so I hit second list 1 minus list 2, so second and then list 2. And when I hit enter, notice it gives me the differences. And notice some of the differences are negative and some of the differences are positive. So sometimes the express lane is faster, but not all the time. Alright, let's go back to our hypothesis test here. We need to start by expressing our mean here. We're going to be looking at the mean difference, so mu sub d, the difference in the times. And the way I calculated the differences in the times is I took the times from the express lane, so I'm going to use a subscript of e here, and I subtracted the times from the regular lane. So the true mean difference in time between express lanes and regular lanes would be found by doing this calculation. Our null hypothesis is that there's no difference between the two lanes, that it takes basically the same time for each lane. So no difference would be mu sub d equal to 0. And here we have to be careful. Do we have a one-tailed test or a two-tailed test? Well, I think most people think that the express lane should be faster. So if the express lane is faster than the regular lane, what type of differences would we expect to see? Positive differences or negative differences? Well, if the express lane is faster, this number would be smaller, So we'd take a smaller number minus a bigger number, we'd have a negative difference. So this needs to be less than 0. Could this be greater than 0? Well, if we subtracted in the other order, then we'd have mu sub d greater than 0. So you need to be aware of what order you've subtracted in and whether you want to have this be less than 0 or greater than 0, depending on the situation and what makes sense. So this is saying the express lane is faster. So let's check our conditions. We said random sample was already met because they did a random sample of 15 times during the week. So that condition was met. And you really want to reference in the problem where that's stated. For the sake of time, I'm just writing random and check. Do not do that on the AP exam. Next, did they sample less than 10%? Well, yes, they did. Obviously, they could have gone to the store an infinite number of times. Well, not really infinite, but in theory infinite. That condition's met because there's clearly more than 150 times when they could have gone to the store. So that condition's met. And then, is our sample size greater than or equal to 30? Well, that condition's not met because we only have 15 pieces of data here. So what we need to do is go to our calculator and look at a normal probability plot of the differences or a histogram of the differences to see if it's reasonable to assume that the population distribution of differences is approximately normal. So let's go to our calculator for that. And we hit second, stat plot. And here I have a normal probability plot. Let's do a histogram this time. I have 15 pieces of data. So that's a bit more data than we had collected in class the other day. We only collected 8 pieces of data in class, so there a normal probability plot was probably more useful. But let's look at a histogram here. We'll do zoom, option 9, and there's definitely more data in the middle, a little bit less on the ends. It's reasonable, there's no outliers or strong skewness here, so it's reasonable to assume that the data, it's reasonable to assume that the population distribution of differences is approximately normal because our histogram showed no strong skewness or outliers. So the histogram showed no strong skewness or outliers. So T procedures are valid. And on the AP exam, I would recommend drawing a little sketch of what you saw on your calculator screen. So we had something I think that looked a little bit like this, if I recall. And you don't even have to put a scale or anything like that, just a little sketch. Alright, so now we're going to calculate our test statistic. We're doing a paired t-test, so I'm naming the test. But the interesting thing is for a paired t-test, we're going to use the exact same formula that when we did a one sample t-test. We're going to do our sample mean differences minus our hypothesized mean difference, and then divide it by the standard deviation of the differences over the square root of our sample size. So we can get these values from our calculator by doing a one sample t-test. So let's do that. Or not a one sample t-test, I'm sorry. One variable statistics. So stat, calc, one variable statistics, we're going to use list 3. So our sample mean difference is 42.7 seconds. So that's saying for this set of 15 pairs of data, the express lane was on average 42.6 seconds faster, and our standard deviation is 84.02, or about 84, sample size of 15. So let's go back and write those values into our equation. This is negative 42.7. Our hypothesized difference is 0 here, and most of the time this will be 0. If you wanted to say, hey, I'm only going to go in the express lane if it's 60 seconds or more faster, then you'd have a 60 or negative 60, depending on the order of your subtraction there, instead of 0. But most of the time, this hypothesized difference will be 0. And our standard deviation was about 84, and our sample size was 15. So if you do this, you should get a test statistic value of negative 1.97 and a p-value of 0.0346 if we do this on our calculator. So let's go to the calculator and see that. We will do a stat calc test, a t-test. So even though we had paired data, we're now looking at the differences. So we've taken those two samples, paired them up, and now we're just really looking at one sample, the sample of differences. And so notice our calculator's already filled in our sample mean, our sample standard deviation, and sample size for us. And I want to see if this is significantly less than 0. So we'll go down here to calculate. And notice our p-value is 0.03. As I said, our test statistic is negative 1.97 approximately. So that means that at the alpha equals 0.05 level, what are we going to do? Well, if the p-value is less than alpha, we're going to reject the null. And we're going to note that 0.05, or actually the p-value, 0.0346, is less than alpha 0.05. So we have our conclusion in statistical terms, but what does it mean in non-statistical terms? What was our question? Well, we had to see if there was convincing evidence that the express lane is faster. They wanted to see if the express lane was faster. So do we have convincing evidence? Well, we rejected the null hypothesis, so yes, we have convincing evidence that the express lane is faster. So one of the questions that you might ask yourself then is, how much faster? And to answer that question, we would do a confidence interval. So let's do that real quick. And we're going to go down to intervals. We're going to go down to option 8, t-interval. And notice our calculator has already filled in our sample mean, sample standard deviation, and sample size. But we need to think about the confidence level. So we had an alpha level of 0.05, which means 5% was all in one tail. And if you think about it, confidence intervals are based on constructing on either side of the sample mean, and that's a two-tail situation. So we need to think about, actually, if we had a two-tail situation, we'd have 0.05 in each tail. 0.05 in each tail is 10% of the tails, 90% for our confidence level. So in other words, with a two-tail test, we have to be, we would just say 95% if our alpha level was 5%. But because this was a one-tail test, we have to make this 90%. In other words, we had an alpha level of 5%, that would be 5% on each tail, 90% for our confidence level. Let's go down to calculate and see how big a difference this really is. Notice 0 is not in the interval, and that's consistent with our hypothesis test. But notice the true mean difference in wait time might be over a minute, about a minute and 20 seconds, or it might only be about 4 seconds. So there's quite a bit of variability there. So your test right now will still be held on Friday, even if we have a snow day tomorrow. However, whether we have a snow day on Thursday or not, with your test happening on Friday, I'm going to allow it to be an open notes test, not an open book test, since your book is an ebook and you could communicate with each other online during the test, but it will be an open notes test. So make sure you have your questions ready. If we have a snow day tomorrow, I will answer any questions that you send to me via email, and I will put together a little review session based on your questions and some other things that I think would be good to review. So feel free to email me any questions you have. And if you're feeling really, really stressed about this and do not want to have the test on Friday, please send me an email individually and I will consider those on a case-by-case basis. But I'm guessing most of you would rather get this test done before spring break. Thanks. Enjoy your day off.